So I won't talk long because I want to get Jane up here, but I did want to talk a little bit about what live virtual and constructive training is, and why we sponsored the project that Jane has been working on. Live training, we like to say everything is real except the bullets, so it becomes a giant game of laser tag, and we do outfit all of the people, all of the weapons, all of the tanks and the equipment that they use so that you can tell what has been hit, what hasn't been hit. And because of that, we use some computers to track and keep score and to observe and be able to give feedback on what occurs in the field. Virtual training is what you think of when you think of a flight simulator. It's something that you're going to get in. We do a lot of helicopter simulators, tank simulators, other types of driving training. So you climb in it and it surrounds you with a virtual world. And then constructive training is the stuff that is strictly computer-based. When you're using it, you know you're sitting in front of a computer screen and you're making more analytical type decisions. So the group that I work with does not make products. We maintain systems. We help people operate the systems. So we're out there in the field working with the user to make sure that their training exercises go well. So to that end, we're looking for ways to reduce costs, improve performance, and then also make better use of all of the equipment that we're maintaining. A lot of the work that Jane's going to talk about occurred at the Joint Readiness Training Center, which we call the JRTC, and it is in Fort Polk, Louisiana, which is one of those places that you don't even necessarily want to visit. So on that, we sent Jane there twice, and she's going to come up and tell you about how we use the system characterization to help find ways to improve the utilization of equipment there.
So I am Jane Orsulak. I'm going to talk about an approach that we've been applying to looking at legacy systems and really making our architectural changes and decisions going forward based on information that we're gathering from the existing system. So characterizing how this current system performs and its capabilities as a starting point and a foundation for future architectural decisions. Business process improvement is a technique that we rely on very heavily. It's a great way of analyzing the people, the processes, and the technology that's currently operating in the existing system. So we fully leverage the whole suite of capabilities from that entire set of practices. Also, if we're trying to optimize our performance, we have to know how that performance is being measured. Many times it's very difficult to quantify or to come up with a specific measure. And we're going to talk a little bit about some of the approaches that we've been using to try to assist in that. But if you don't know where you're going, it's really hard to chart a path towards achieving that. And finally, the next challenge that we face in this particular program set is that we're not just dealing about IT systems, but we're really dealing about the services that we provide in order to support our warfighter and their training exercises. So it is about the technology, it is about the instrumentation of the systems, but it's also about the people who have to perform maintenance, the people who have to get out into the field, looking at maximizing their schedules and getting the most out of those individuals. So a lot of it is the processes as well. So the areas that I'm going to pull from examples are from the Warfighter Focus program, and Julie gave you the long name that the FOCUS is the acronym for. The Joint Readiness Training Center, what we're looking at there are the maintenance activities, and that includes physical maintenance of devices, and it includes the information assurance, patch releases, that type of maintenance, and it also includes looking at long-term replacement and of obsolete equipment and technology refresh associated with that. The depot architecture that we're doing for the training centers at large, there are about 20 training centers, and the depots are at some of them, but not all, and we're looking at what is the optimal architecture for deploying those depots. Should we have one centralized depot? Should we have several decentralized? And if that's so, where should they be? The last area is looking at the crew trainer, and this is one of the aircraft trainers where the soldiers get inside the trainer itself. And we've got a lot of challenges in trying to maintain this fairly physically demanding environment. And maximizing the amount of time that the soldiers have to use the trainers by minimizing the amount of time it takes to do the maintenance on that. I'm also going to pull a couple examples from other areas. The CFS program that I work also does the operations, sustainment, and maintenance for an intelligence processing system. We provide people who support setup of the equipment, help to address any issues that occur during a mission, and also do a lot of preventative maintenance and normal types of maintenance during the off-peak times. And so we're looking at some workload analysis for those. So those are the examples that I'll be sprinkling throughout. I'm going to talk just a little bit about the process and then go into a more detailed description of each of those steps of the process, and I'll pull in the examples at that point. Legacy systems, many of you are familiar with legacy systems. We don't get it right the first time or the second time or the third time, but if we don't step back and look at what this real system is, the way it's actually performing, we don't always make the best architectural decisions going forward. Just because we think a system was being used in a certain fashion by the users doesn't mean that that's what they're doing today. Their needs have evolved, the demands on the systems have evolved. In the case of the Warfighter Focus Program, many systems have been deployed independently through different contractors and so forth, many of which do not communicate together and causing a lot of difficulties in maintaining those systems. We need to consider the cost of not just acquiring the replacements of that system, but how do those acquisitions and those changes in technology, how do they affect the usability of the system, how much it costs to operate, and how much it costs to maintain and sustain that. So it's not just the acquisition costs, not just the fact that this server now, this blade server costs X and that equivalent cloud environment costs Y. But what's the relationship to the cost to operate and then subsequently maintain it? So also performance is a real factor in deciding to upgrade a legacy system. The technology advances have significantly changed over the 10, 15, 20 years that these systems have been deployed. Also, our system operators and users of the systems, their expectations are different. They're using commercial technology in their homes, but what we're dealing with in the defense industry, because of the acquisition cycle, is already 2-3 years behind any current commercial, even when the system is first deployed. We use the terms measure of effectiveness to help us into quantifying the goals of the system. A measure of effectiveness describes what the end user sees as success. They're often very intangible and very hard to describe and quantify, I should say, what they're looking for. For the Warfighter Focus Program, being able to support 100% of the time the operational training missions that are going on is critical. As Julie said, we could have 2,000 to 10,000 soldiers showing up for an exercise. And if the equipment is not ready so that they can perform that training exercise, you've just wasted a whole lot of taxpayer money. So it's imperative that we, have our systems operational and ready. So our measure of performance and a measurable aspect that contributes to the effectiveness is the availability of that system. And then so the availability would be the specific measure of performance for our program. In contribution to that, the various components of the systems each supply their technical performance measurements. These are the piece parts that go together to allow you to achieve a higher level performance measure. For the JRTC, for example, a subsystem may have a mean time to repair of a certain limit, and that's all in fact impacted by the availability of spares, by the training and the technology and the capabilities of the maintainers and so forth. So that falls on us as the contractor providing those services to ensure that we can meet the requirements. Areas that we focus on looking for performance improvements. Clearly, any time that the humans are interacting in the system is an obvious place to look. People do not behave the way that the original designers expected in many cases. The systems have evolved, the needs and demands have evolved. Also, the surge or emergency type non-typical situations are also areas that many systems will break. And so looking at the capacities of the system is really important. So as we go through, system constraints have changed too. That's another area where you would want to focus on looking for improvements. do we need to have a limited resource? Do we need to change that out? Is it constraining how much we can do? Do we need to add extra resources? If we need to have maybe getting our inventory done more timely so that we know exactly what parts need to be reordered, do we need to put mobile equipment out into that particular storeroom so that the inventory maintainers can do a much more rapid ability to do that inventory? Those are the kinds of things we're looking for. And these are all quantified in leverage points. A leverage point, in my terminology, this is not an official terminology, is the areas where you can provide the biggest impact for the least amount of investment. So there are a lot of alternative and potential changes, but we all are limited by an overall budget constraint. And so being able to maximize the specific recommendations that we make to get the most use out of that given budget is really important. And it's also important to notice that it's not always about technology. It can also be about improving the processes or the training, for example. We're looking at one example where we may be cross-training our staff. Currently, we have a situation where we have people who are trained in maintaining hardware, people who are trained in maintaining the software, and people who are trained in maintaining network components. When we start to cross-train them, we can go from having 3 people to having 2. Because the workload is not sufficient to require all 3 people, but the skills were required. So those are the types of things that we've been looking at. Where do we look throughout? Anywhere that change has occurred are opportunities to look for improvements. Have the assumptions about a system changed? Were they assuming that there was going to be a certain training level available to the operators of the system, and that's no longer the case? Has the technology changed? Almost certainly. The technology that was available 10 years ago when those systems were deployed was at a certain level, and today's available technology is going to give you leaps and bounds of performance improvement. But not just the technology, have the rules and the policies changed? Perhaps that's a limiting factor that we need to look at as well. And so everything that has changed is a potential for changing in the future as well. Understanding where the systems came from can help us guide where we need to grow it to in the future. So the process I'm going to talk about is up here. I'm going to just spend a very brief amount of time on the overall process, and we'll step into each of the steps. But the fundamental process is that we want to model the current system that we have today, and we want to do that based on data that's being gathered from the field, from the existing systems. So we want to model the as-is. Then we want to validate that that model predicts today's performance so that we can trust that we can start to make at least some assumptions about future performance. We want to analyze that model, looking for those leverage points, looking for the potential that we can make improvements. Explore those alternatives. What if we did change the number of servers? What if we went from a distributed to a cloud environment? How will that change the overall performance of the system? Finally, we build together a plan of the collection of the individual projects and present that and recommend that for our next steps. So the first step is the data measurement gathering. Anything that we can do to gather data that is based in recorded logs or anything of that nature is clearly the best. Human nature is such that they want to when they self-report, they're concerned about their jobs perhaps. They want to make sure that you believe that they are fully occupied. We're dealing in many cases with the Maytag repairman situation where people have to sit around waiting for things to happen so that when something bad happens, they're immediately available to do some response. That means that there intentionally will be downtime. People are very sensitive about that, and when you go and interview them, you don't always get truthful or accurate, I should say, accurate results. So going back and pulling any of that data from logs, from reports and things like that is much more superior. However, that's not always the case, and so we can also observe or interview the operators and the maintainers and the users of the systems to gain that insight. Not only do we have to understand the using of the system, but we have to understand the demand on that system. When you start looking at historical data and you're seeing a certain number of work orders that have been produced over time, well, what's the demand on the system that would result in that? Maybe the increase in work orders was due to poor equipment. Maybe it was due to the fact that they deployed 10 more systems in that time period. And so therefore you had more equipment to do maintenance on. So without understanding the demands that go along with the usages of the system, it's hard to make that correlation. So the example that I have here is a workload analysis that we were doing for one of the aircrew trainers. What we did was we went through and did an analysis to describe every task that the operators and maintainers were performing. We used data that we gathered from the work order history to determine how many failures were in the system so that we understood the frequency that the bad things happening would actually occur at. We used interviews from the operators to get a sense of the minimum, the maximum, the most likely duration for the various tasks. And we also characterized the individual resources, the people who were doing the maintenance, to understand their training, their skills, their proficiency in the various aspects that are required. And then finally, we characterized the environment. We described the 24-hour maintenance cycle, the daily cycle of activities. We bounced that against the training cycles that are required to support the training missions. And then we ran all of this through a discrete event simulation tool, analysis tool, to help us understand where the peaks and the valleys were in the workload. Once you understand the data and you've gathered that, then building a model is the next stage. In some cases, we want to do a paper model. Workflows are good examples of things that using not necessarily paper, but maybe it's a Visio or maybe it's a business process modeling language, but it's a static model representing the various activities and the workflows. In some cases, we do a dynamic model using simulation to help us better understand the dynamics of a situation where that's important. We've interviewed our analysts to get our maintainers to get the various steps that are occurring and the activities that are going on and the relationships of those steps to one another. We then would build a low fidelity model. Since we're looking to use these analyses to help guide where improvements should be made, investing a lot of money in a really in-depth model is not going to cut it with any of our business people. They want quick answers. They don't want to wait 3 months. They want to wait 3 days maybe. Usually they give us 3 weeks, 4 weeks. So we don't have time to build a very long, extensive model. And in many cases, it's really not needed to get the insights. The examples that I show here are looking at workflows for maintenance activity. The actual maintaining of the hardware equipment is one of the workflows. Maintaining from the information assurance perspective, rolling out software patches and things of that nature. And then a longer term cycle where we're looking at technology refresh, where the projects may be months long instead of days. So we're comparing these from one site, and now we're going to some of our other sites that do similar work to see if they have the same processes, and if they're different, where are they, what's the best of the breed, so we can bring that back as an overall recommendation to improve the processes for all the sites. After you've built the model, you need to build trust in that model, and that's through validation activities. If you can't predict today's performance, how can you potentially predict tomorrow's performance? So the first step would be to make sure that with the data that you've gathered and the characterization of the system that you've made today, that the model is actively predicting the performance that you expect for today. You can do that by, as we were talking before, analyzing the current workload, current characteristics of the system and in the environment, and then using that to predict the workload, and then comparing that against subject matter experts' opinion about, is this a correct approach? Is this matching reality or not? Running Monte Carlo analyses of the simulations is a great way to understand the level of confidence that you have in that system, how much variability is introduced, and where the confidence intervals are on your results. Very powerful in being able to help explain to the consumers of the reports how much confidence you have in those models. So the example that I have here is a discrete event simulation that we did for the depot modeling that I'd mentioned earlier. We were looking at whether or not we should move from a decentralized to a centralized depot approach, and if we wanted to readjust where the depots that we currently have, where they would go. So that's what you see there. We also took a lot of effort to go back to the subject matter experts and make sure that as we were running through the various scenarios in that simulation, that they reflected what the subject matter experts expected the system to perform. Any updates that you get as a result of that analysis need to get fed back in, and then you can feel confident that the model is valid. One other thing that you should be considering too is that if you're making a major change in technology, for example, you are going from maybe a distributed to a cloud environment, you aren't going to have necessarily any performance data related to the cloud. That's a new technology that you're introducing. So going and finding another similar program or industry result that can validate that the performance, can help you validate the performance of that new technology in your system. That's going to be something that you're going to be less confident in, but you still need to do the best you can in gathering that type of information. Then looking at that model, using the model itself to explore and analyze the existing performance. So being able to adjust the steady state and understand where the peaks in the valley are for typical operations. But what if you start to increase the demand on the system? What if you change a constraint? What if you add an extra server? Well, how does that impact the overall performance? Looking for those leverage points where a small change in the architecture results in a measurable change in your measure of performance. The example that I show here is a workload analysis that we were doing for a mission support operations. We have staff that is on a daily 24-hour cycle where there's a 10 to 12-hour mission overlaid on top of that 24-hour cycle. Our operators, our maintainers have some pre-mission work where they set up the equipment and they verify that everything's operational before the mission begins. Then there's some activity that goes on during the mission, and then there's some cleanup work at the end. And in between the mission is when they do all their preventative maintenance and all of their things that scheduled maintenance or unscheduled maintenance that could be delayed. And what you're seeing is a graph of the various priority of tasks that are occurring over that period. And you can see for most cases, everything's getting done. We have a period where we only have two maintainers towards the middle right of the graph that looks really flat there. And what's happening is that with the two people, they're fully utilized during that period of time. And through the analysis, we can determine what tasks are being dropped. Now, maybe it's a task like their training, extra training activities and things like that that don't have to be done to support that mission. But those are the people who are on that same cycle, that same shift every single day. And if they're never getting time to do their training is going to suffer. So it may not be timely critical for that particular day, but overall it's an issue. And that has given the system designers some really good insight as to where they might want to tweak. So finally, once you have the model and you understand the current as is, now start looking at what if we change things? What can we do differently to make an improvement in the system? This is where we'd want to explore the system constraints and introduction of technology, changing system capacities, and things of that nature. Understanding how these incremental projects relate to one another is also important. Sometimes technology relies on other capabilities to be deployed. Let's say we had two applications that were mobile. For example, if we wanted to put a mobile scanner out in a remote stockroom so that they could automatically do their inventory without any delays. Well, that requires not just the technology to do the scanning of the inventory, but it requires the back-end processing of all of that as well. Those two projects that would then depend upon each other. But now that you've got the back-end for this one critical thing, maybe there's other mobile applications that can piggyback on top of that, and you link your projects that way. So there's going to be a series of these. Obviously, when you're dealing with a legacy system upgrade, you've got budget constraints and you cannot do everything. So packaging the upgrades together in a logical fashion is an exercise that you'll need to go through. So when you come up with that final result after doing your trades and doing your analyses, you can feel confident, though, that you've made those decisions based on good data that you've obtained from the as-is system, and you've got, and it's been substantiated with your analysis that you've been doing through the modeling. So in summary, it's really about making fact-based decisions and using the leverage that you have in the existing system to make those recommendations going forward. If you don't know what success looks like, you really can't get there. And if you don't measure that success, it's hard to determine whether the changes that you're recommending are going to improve that or not. And finally, don't forget about the people and the processes. Clearly, technology is going to be refreshed. Clearly, you need to bring in technology to replace obsolete equipment. But don't forget about the people and the processes, which can influence the success of a program just as much. Exploring that as-is system is very helpful in identifying those various leverage points, and then looking at the pros and cons of your package approaches will then lead you to the most cost-effective upgrade path that you could get to. And I think we've got a couple minutes for questions. Any questions? Yes.
How much do you have problems with cascading changes? You see something, you say, oh, I get some leverage here, and you make a change, and then you find out you need 3 other changes.
Well, that's the whole part of if you can analyze that within the model, you get a better understanding of what those cascading changes are before you start to deploy them. And that's the whole idea, exactly. Yes.
Do you ever have to make any trade-offs between intuition versus measurement? Right? You have time constraints on on how much time you have to build your model.
Well, sure, absolutely. And that's where the subject matter expertise and the architectural judgment comes in. Clearly, a model is only as good as the data that goes into it. And the validation step helps to build the trust in that model, but it's a confidence interval. It's not a 100% solution. So the architect's vision and understanding and belief and understanding of that model will help drive those decisions. The better facts you have to back up your analysis, the more you can trust it, but it doesn't completely do away with the judgment of the architect involved. Yes.
Soldiers are ingenious in their ability to find new ways to break things. So how much of your analysis, it would be easy for the exercise, people running the exercise whom you support to say, just fix the equipment. How much access do you have into how the exercises are then conducted in order to increase your availability through proper, understanding unexpected uses of the equipment?
I'm going to let Julie answer that one.
So we're really involved in most of these exercises. We are often acting as the observer controller, and we run the video camera, so we see that. But what we've found is while soldiers can get really creative with how to break things, things are only breakable in so many ways. So at some point it becomes, do you repair it or do you replace it? And that we're able to, track and get statistical models of the level of repair that is needed rather than looking at how it got broken. We're looking at, what do we need to do to repair it? That helps. Sure.
And there was a question in the back there.
Guilty. I was just curious, is this a funded part of the maintenance activity to continually monitor what needs to be modernized and how?
Yes. We are part of what we're responsible for doing in terms of maintenance, is providing life cycle plans for obsolescence, but also for performance improvement or utilization improvement.
Time for one more.
One more question. Was there one more question over here? Yes.
I just had a quick question about recommendations for managing kind of the people aspect. You touched on dealing with legacy systems and possibly certain jobs may be obsolete, not quite getting the truth from people as far as what you do and how it may impact the system overall. Is there any recommendation on kind of, okay, when you step into this type of environment, these are some of the things that you need to do to best manage this sometimes difficult situation?
That is a real challenge, and on not the Warfighter Focus program, but one of the other ones that we were dealing with, we're faced with that exact issue because we know we're a little bit overstaffed on this particular program, and we're looking for ways to cut people on this particular job, not on Warfighter Focus. And when we went to interview people, that was a real issue because they're very protective about their jobs and so forth. And I mean, you can't go without interviewing them because that is a great source of data. But what you can do is cross-validate, get a number of people that you interview, and so you're not just getting one person. Get management to review the assessments and interviews to give their feedback as to whether or not they're appropriate or they need to be, adjusted in any way, and then tie things to measurable events wherever it's possible. For example, we were looking on the Warfighter Focus of how many work orders were written. So that is a way for us to know how many maintenance activities occurred. And then we could, cross-correlate that to the interviews to say, are they giving us, good estimates of the frequencies of these activities? And then we could help to scale the interpretation of that. But you really cannot trust that data 100%. And the best you can do is to tie it to something that is measurable outside of the human response aspect of it, because it is a real challenge. And the other aspect of that is that when people are doing jobs like a Maytag repairman, where there's not sufficient work to keep them 100% busy, they do one of three things. The first thing is they'll stretch the work to fill the available day. The other thing is they may do the work in the normal time, but do something else when they're not busy. So that's where you'll see like a receptionist that's reading a book while she's waiting for somebody to come into the office. And the third thing that they may do is they may take a lot of initiative and do things that are outside the scope of their job. They're all equally valid. I mean, you can't really argue because in each case, they're getting the job done. But what is hard then is to interpret from that information exactly how much time it takes is a normal expected amount of time to do that task. So that is a challenge, and it's a very difficult to overcome challenge. The best we can do is to look at the data and understand that there's uncertainty in it, and don't over rely on those reports.
I want to dovetail just a minute, because for JRTC, one of the things that we really wanted to get across was we were not trying to cut staffing. We have more work in that area than we can do, and we can't necessarily increase it, but if this portion of a job goes away, we're going to make sure that there is some more work coming in to fill that person. And that was actually a challenge to get across as well, in a way that people might believe it.
Right.
So with that, we're going to have to move on to the next one. Thank you very much.